Okay. So yeah, I'm going to start Timoshenko beam come basically frame finite element. So I'm combining the two together. Timoshenko beam. It's actually frame element rather, but based on Timoshenko beam theory. So Timoshenko beam slash frame finite element. So as the name suggests, this is actually based on Timoshenko beam theory. So earlier we discussed Euler-Bernoulli beam finite element, which is based on Euler-Bernoulli beam theory, which assumes that normal to the middle surface or neutral surface remains normal after deformation. Whereas in the Timoshenko beam theory, this assumption is actually relaxed. So it becomes applicable to moderately thick beams. So that is why we use this Timoshenko beam finite element. So in this, essentially again, what we are talking of a beam. So let's say beam with a coordinate capital X along the length and Y along the thickness direction, and then this beam deforms, and we are going to assume the axial load also, so it gets stretched. So this will be the deformed configuration of the beam. And let us say that when we have a total beam length, so let us say the total length of the beam is here, this capital L is length of the beam, not of the finite element, and let us say h is the height of the beam. So if we look at the basic assumptions made over here, so the assumptions are: number one, main thing is that beam is moderately thick. Actually, other things are just the essentially the implications of this moderately thick beam. So main assumption is that beam is moderately thick. And when we are saying moderately thick, so what I mean is to say that L by H is smaller than 20 typically for isotropic beam, where L is the total length of the beam, capital L. It is not the element length. So this is the main assumption, and the implication of this is that normal to the middle surface, normal to the middle surface remains, rather it does not remain. So yeah, when I say remain, so it is for the Euler-Bernoulli. So normal to the middle surface does not remain normal after deformation. So in the initial configuration, what I am saying is that let us say this is the beam and this is the middle surface. So if this is the normal, so initially this angle is 90 degree. When we look at the deformed configuration of this, so it does not remain normal, but if the normal is somewhere here, then this line would go to something like this. So this angle is not 90 degrees. So this is not equal to 90 degree. So the normal does not remain normal after the deformation of the beam. So normal to the middle surface does not remain normal after deformation. Does not remain normal to the middle surface, basically deformed middle surface. And third assumption is that plane cross section. So whatever, if we take the cross section as plane, so they remain plane. Plane cross sections remain plane after deformation. So yeah, these are these two, second and third, are the implication of the first assumption that beam is moderately thick. So you basically have essentially these implications from that. And so now to develop the theory, that is we go with the displacements, then strains, stresses. So let me sketch, give some details. So when I'm taking details, so let us say, I think let me draw it below. So let me draw over here. So this is the beam before deformation, and after deformation, this beam takes a shape like this. So this is the beam after deformation, and coordinates are, I'm still using capital X and capital Y. So now if I take no any initial normal and a point at a distance y from the middle surface, so this coordinate is y, and this is the deformed center line. The dotted line is a deformed center line. So now the beam is subjected to both axial as well as the transverse load. So the middle surface actually gets stretched. So that is why this point will move somewhere. So this line will move, so it will go somewhere there. And if I look at a line parallel to the initial configuration, so this is the line parallel to initial. This is line parallel to the initial configuration, and normal to the deformed surface would be something like this. This will be normal. You can say this angle would be 90 degrees. So here the various lines, if you see, this is the undeformed configuration. This is the deformed configuration, and the various lines, if you see, so here what I have sketched is actually this is the yeah. So what I wanted to show is that this is the, if you look at this one, this is the deformed configuration of normal to undeformed middle surface, of normal to undeformed middle surface. So now that is one. If you look at the this line, no, if I let me, so this line, so this line is basically normal to deformed middle surface. So the angle between that line and the tangent to the middle surface is 90 degrees. So this is normal to deformed middle surface. Normal to deformed middle surface. And one more line I have drawn, which is normal to undeformed. Now this dotted line. So the dotted line is also, let me, so over here, this is normal to deformed undeformed middle surface. Normal to undeformed middle surface. So these are the various lines. Now if you look at the no distances, so this line has got displaced by an amount u naught. And then if you look at the various rotations, so this is the actual, initially this is the line, this line has gone over here. So if you look at this angle is what is the now rotation of the normal. So this we call as theta z, rotation of the normal. And if you look at basically this angle from here to here, this total angle, this is what dv by dx, that gives no the line which is normal to the deformed middle surface. So if you look at no this difference, that is if you look at no this angle over here, this angle, this one, this angle is what is the difference. So it is basically dv by dx minus theta z, and which is actually the shear strain, that is the shear strain. So no that is what you have. So if I just draw the exaggerated view of that, so you have this line over there, then you have the this line which is actually the which was initially normal to the undeformed configuration, but it is no longer normal to the deformed so this is the line, and this is the line which is normal to deformed middle. That is a actually imaginary line which is drawn to the virtual to the middle surface, virtual line drawn normal to the middle surface, and this is the middle surface. So what I have said is this angle is theta z, this angle is dv by dx, and this difference, no, that is this angle, is what is dv by dx minus theta z, and this is known as transverse shear strain. So yeah, this once you understand the deformation, so basically one is the line. I'm so if I use different colors, which I didn't do. So initially, if you look at this line is the one which has basically gone over here. That is this line. So this is the actual no, line which was initially normal to the undeformed middle surface, has deformed in this manner, and it no longer remains normal. And then we have drawn a virtual line which is normal to the deformed middle surface. So this line is the virtual line which is drawn normal to the middle surface, deformed middle surface. So this angle, no, this angle is 90 degrees. Uh, Yeah. So now if I talk of displacements, so the way we discussed earlier, know the displacement component. So we know that we have axial displacement u, which is a function of x and y. Now it is, earlier it was no, if you remember in the Euler-Bernoulli beam theory, it was minus y into dv by dx. But we have now this no, the displacement of the point on the middle surface y equal to 0, that has got moved by a distance of u naught. And then if I take this point, say if we take this particular point, this point what I am talking over here, so this point has gone somewhere here. So if you look at this distance, the distance from here to here, this is minus y into theta z. So first this point is at a distance of u naught, and then you subtract this distance minus y into theta z, you get the total displacement. So this would be u naught into x minus y into theta z, which is a function of x. U naught is a function of x, and theta z is also a function of x, and this y coordinate comes. So as usual, we call this as axial displacement. And then we have another displacement, transverse displacement b, which we assume to be function of only x, and we call that as the transverse displacement. So this is transverse displacement. Now once we have defined these displacements, so then we go to strains, and then the strains are epsilon xx is del u by del x, which is basically du naught by dx minus, so you are just differentiating this with respect to x. So this u is a function of x and y, that is why I'm putting partial derivative. But then when you go here, this is a function of only x, so I'm putting total derivative minus y into d theta z by dx. So this is the normal strain along x direction. So as you know, this is normal strain along x direction. So normal strain along x direction. Then you have now earlier in the Euler-Bernoulli beam theory, or if you remember the frame element based on Euler-Bernoulli beam theory. So we had the strain was du naught by dx minus y into d2v by dx square, and the shear strains were 0. But now we will have this transverse shear strain gamma xy, which is defined as del u by del y plus no del v by del x. So this is by definition. Now if you put the value del u by del y, so this is the expression for u. So this is only function of x, its derivative with respect to y will be 0. So only we will have this term, so this will be equal to minus theta z, and v is only function of x, so we will have here dv by dx. So this is known as transverse shear strain. Transverse shear strain. And then of course the other shear strains like gamma yz and gamma zx, these are actually 0. These strains, these strains are 0. Then no, we once we have defined the strains, then we talk of no stresses. So the major component of stress is going to be axial normal stress. So before I write the relationship between stresses and strains, we talk about the material. So we are assuming that material is linear elastic, isotropic. Material is linear elastic and isotropic. Additionally, we assume here, earlier, no, if you remember, for the either the truss element or the Euler-Bernoulli beam element or the Euler-Bernoulli beam theory based frame element, we had only one non-zero component of stress, that was sigma xx. But now we'll also have tau xy as non-zero stress. So I am calling this as generalized uniaxial state of stress. Generalized uniaxial state of stress. So for this, now you know the sigma xx is equal to E times epsilon xx. So this because epsilon xx we have defined as du naught by dx minus y into d theta z by dx, and epsilon yy from the Poisson's effect, epsilon yy would be minus nu into epsilon xx, and if similarly epsilon z will also be minus nu into epsilon xx, will be epsilon xx. So this comes from the Poisson's effect, and the transverse shear stress tau xy would be equal to g times gamma xy, and g times gamma we have defined as minus theta z plus dv by dx. So this is a transverse shear stress. The other two stresses, that is tau yz and tau zx, these will be 0 because the corresponding strains are 0 as written over here. Now one thing you will observe that when you look at this tau xy what we have got, so this is independent of cross sectional coordinate, that is y. So that means it is constant through the thickness, constant through the thickness. Whereas if you look at the actual transverse shear stress distribution, actual means if you look, let's look at the rectangular cross section beam, and if you look at the transverse shear stress distribution, it's actually parabolic, which is zero at top and bottom. So the actual transverse shear stress is parabolic, at least parabolic. There can be other variations. Actual transverse shear is parabolic in rectangular cross section beams. Cross section beams. So this, no, you must have, no, if you would have done transverse shear stresses in beams, you would have actually, learned about this variation of transverse shear stress. So now, if as a special case, if I want to look at, again, want to go back to Euler-Bernoulli beam theory, so you would notice, know that for Euler-Bernoulli beam theory, although no, in this discussion we are concentrating on Timoshenko beam theory, but I just want to tell you that as a special case of this theory, we get Timoshenko beam theory. So for Euler-Bernoulli beam theory, tau xy, which is g times gamma xy, this is actually equal to 0. So as you see, this is g times minus theta z plus dv by dx. So if it is 0 means then theta z is nothing but basically dv by dx, because no gamma xy is 0, and that means minus theta z plus dv by dx has to be equal to 0, and that gives you theta z is equal to dv by dx. And that means that when you look at these normals, so this is the actual normal to the deformed middle surface, and this is the hypothetical line which is normal to the deformed middle surface. So these two will coincide. That means no, this theta z and dv by dx are equal. No, this theta z and this dv by dx, they are equal. So this difference is 0. dv by dx minus theta z, this difference is 0. So then these two lines coincide. That means the actual normal remains normal to the deformed middle surface, and that's the basic assumption in Euler-Bernoulli beam theory. So you can get that as a special case of Timoshenko beam theory. Now, having defined the displacement, strains and stresses, I also want to define what we commonly used and are referred to as axial force, shear force. So axial force, let me denote by capital Q, and shear force I am going to denote by S subscript Y, and bending moment I am denoting by capital M subscript Z. So for defining these, I am going to derive these from the distribution of stress. So if you take a beam, I am assuming that the deformations are small, so the deformed and undeformed configurations are basically nearly same. So this is x and this is y. So if you look at the stress distribution, so one is sigma xx. Sigma xx is function of y. So let us say that no, it is varying as a function of y, and because you have axial load also, so it may not be 0 at y equal to 0. So you may have some distribution like no, the distribution may be something like this. So this is the distribution of sigma xx. That is how this normal stress is going to be there. In addition to this, there is a shear stress. So their shear stress is on, because here if you look at this section, outward normal is along positive x direction. So I have shown the positive normal stress sigma xx along positive x direction on the top surface. So this is obviously negative, and similarly positive shear stress tau xy would be positive on the positive face along positive y direction. So this is no, this is basically your tau xy. So both here, this is positive normal stress sigma xx, and this is a positive shear stress tau xy as per the sign convention. So if you look at the axial force, how we define this axial force Q? So for that we integrate the sigma, we take the cross section of the beam, and take this is basically your y coordinate, and then this may be your z coordinate. And if you take a small area dA over here, so the sigma xx into dA becomes a force over a differential area, and then we integrate it over the entire area, so we get the axial force, that is net no axial force. So this can be written as A, and sigma xx we have written as E into du naught by dx minus y times d theta z by dx dA. So this is the axial force. And now if you look at this integral, so the first term is independent of the cross sectional coordinate, as you see here. So we will have, and the no du by dx is a function of x only, and assuming that E is independent of y, that is material is not changing along y direction. So of course if it is changing, then you'll have to account for that in this integral. So now you have the integral dA, that will give you simply A. So the first term will become E into A into du by dx. And if you look at the second term, it is the integral y dA. And integral y dA for a symmetric cross section would be actually 0. So then axial force is simply Ea into du naught by dx, and the reason is that since integral y dA is equal to 0 for cross section symmetric about y equal to 0. So this integral y dA is 0, and therefore you get q is equal to Ea into du by dx. So finally you get know this as q, which is Ea into du by dx. And you would remember that this is nothing but actually secondary variable. So this same thing we are no this is the same quantity, and we refer to as secondary variable. So this is the axial force. Then we define the shear force. So the shear force, no, we are trying to get the now relationship. Earlier, if you remember, in the Euler-Bernoulli beam theory, the shear force was minus d by dx of EIZZ into dv, no, d2v by dx square. And now we are writing, because we have know the rotation of the normal as an independent variable. So we are going to relate this shear force Sy, which will be integral tau xy over the cross section, over the entire cross section. And you know that tau xy g into theta minus theta z plus dv by dx, which is constant through the thickness. So we simply write here, no, this integral will be give you ga into minus theta z plus dv by dx. So this is now the shear force. Earlier in the Euler-Bernoulli beam theory, this was minus d by dx of no ei d2v by dx square. But now it is simply ga minus theta z into dv by dx. So earlier in the Euler-Bernoulli beam theory, you remember v was a primary variable, dv by dx was a primary variable. But now here you see this dv by dx is appearing here in the definition of shear force. So this is kind of secondary variable. Of course, this whole quantity we refer to as secondary variable. So this is secondary variable. Shear force is just also secondary variable. Then if you look at the bending moments, if you remember earlier I had defined. So here no you are having a, no, if you are taking a small area, then sigma xx into dA is the force, and then you want to calculate moment about z axis. So this is x, this is y, and as per the right hand triad, z axis will be coming out of the screen. So this is z axis. So this sigma xx into dA will give you the moment about negative z axis, but the bending moment on the positive section, that is when outward normal is along positive coordinate direction, the bending moment is positive about positive z axis. So we introduce a minus sign the way we did earlier. So we write here, no, we put minus, and no, sigma xx into dA is the force, and into distance y gives you the moment, and a minus sign gives you the positive bending moment on the positive z side. So this relationship also indicates that due to positive bending moment, there is going to be basically negative stress on the top side, and due to negative bending moment there would be positive stress on the top surface of the beam. So in this definition now we already know sigma xx is E into du by dx minus y into d theta z by dx. So if we put the value we will get y into E, and then we have du naught by dx minus y into d theta z by dx dA. So now in this again, if you look at now the first term is integral y dA. So we are taking the same symmetric cross section. So since integral y dA is 0, the first term would become 0. And second term this minus minus becomes plus. And then you have integral y dA, and integral y dA be defined as izz. So this will become e izz into d theta z by dx. Here izz is nothing but integration over the cross sectional area y square dA. And this is again secondary variable. I know the bending moment, as you know, this is also a secondary variable. Now if you remember in the Timoshenko beam theory, this bending moment was Eizz into d2v by dx square, but now theta z is independent, so it's the basically first derivative of that. So this is what you get as the bending moment. Now we also, because no, we sometimes deal with the differential equations, so let's look at the uh, know the differential equations, so equilibrium equations. So now the equilibrium, for the equilibrium equations, let me draw the free body diagram of a differential element. So if you look at the equilibrium equations, so for that I am taking a small differential element of the beam of, let us say, length delta x, and the forces are, no, there is a axial force per unit length, and there is a transverse force per unit length, that is qy, which could be a function of actually x. In addition to these, because we are cutting the beam over here and cutting the beam over here, there would be right left side some portion of the beam, there would be right side some portion of the beam. So those portions are going to exert forces on this. So there would be x. Now this is a, now our coordinate system is, this is x, this is y. So outward normal to this section is along negative x direction. So the positive forces are going to be along the negative coordinate direction. So the positive axial force would be in this direction. Let us say that is q. Positive shear force is going to be in the negative y direction. So that is, let us say, sy over here. And then the positive bending moment is going to be about negative z axis. So this is a positive z axis. So the negative z axis moment about negative z axis would be like this. So that is mz. And this q, sy and mz, that is axial force, shear force and bending moment, they are functions of x, so they will change. So on the right side, if you look at the outward normal to the section is along positive x direction, so the positive forces and moments are going to be about and along positive coordinate direction. So the positive axial force would be in this direction, but because of the variation it will have some increment, so we will have q plus delta q over here. Positive shear force would be in the positive y direction, and that would be because the section, on the cross section is a positive cross section, because outward normal is along positive x direction, so that is sy plus delta sy. And positive bending moment is going to be mz plus delta mz. Now this moment is about positive z axis as per the right hand screw rule. So now if you look at the equilibrium equations, so one is sum of forces along x direction equal to 0. So if you look at the forces, this is along negative x direction, so minus q. This force is along positive x direction, so we have q plus delta q. Then another force is this qx, so that is qx force per unit length into length, that is delta x, is equal to 0. So then what we do is we know this q and this q get minus q and plus q get cancelled. So we have delta q plus qx into delta x. So what we do is we divide it by delta x and take the limit delta x going to 0, because we want to derive the equilibrium equation which is valid at a point. So then we have limit delta x going to 0. So we will have delta q by delta x, and then here we will have qx this will be equal to 0. And you, as you know, by definition of differential, the first term is then dq by dx plus qx is equal to 0. So now we know that q, we have already written that q is ea into du by dx. So then this becomes d by dx of ea into du naught by dx plus qx is equal to 0. And let me number that this as equal. So this is one equation. So now if you see in the problem as a whole, if you look at the, when I talked about these, the displacement approximations. So if you look at the unknown variables are actually now three: u naught, axial displacement along the axial direction, and theta z is rotation of the normal about z axis, and bx is the transverse displacement. So these are three unknown variables. So there has to be three differential equation. So this is one of them governing basically the variation of u naught within the beam. Then another equation would be sigma Fy equal to 0. So if you look at all the forces in this free body diagram, so on the left hand side you have this Sy which is along negative y direction, so minus Sy. Right hand side you have this along positive y direction, so Sy plus delta Sy. And you have the transverse force, this Qy, so which is Qy into delta x. And then there are no other forces along y direction, so this must be equal to 0. So now if know the similar logic, these two cancel, then we divide by delta x and then take the limit delta x going to 0. So you get basically this dsy by dx plus qy is equal to 0. And we have written earlier know that sy ga into minus theta z plus dv by dx. So this can be written as d by dx of ga into minus theta z plus dv by dx plus qy equal to 0. So this is the another differential equation. Of course, in this case you will see that now this differential equation involves only one variable, that is u naught. But this differential equation involves two variables, theta z and basically dv by dx. So both the variables are involved in this equation. Then the third equation we get, so let me, in this free body diagram, let me denote this point as point A. So we write the moment of all the forces about z axis passing through point A equal to 0. So you will have sigma m a z is equal to 0. So this will give you again the same logic we apply. So this moment is about positive z axis. This is about, although it's this side also, this is a positive bending moment, but this is a moment about negative z axis, so we put a minus sign. So we have basically minus mz plus mz on the right hand side plus delta mz. So these are the contributions due to mz and mz plus delta mz. And then you have shear force. So this shear force is passing through point A, so moment of this is going to be 0, but this will produce a moment about positive z axis. So we will have plus sy plus delta sy into delta x. And you also have the moment due to distributed force qy. So the force is qy into delta x, and then the distance from the point A is delta basically resultant of the force qy will be at a distance of delta x by 2. So this is the total moment, and that's all. So all this must be actually equal to 0. So again what we do is these two terms get cancelled and we divide the whole thing by delta x. So delta mz by delta x, in the limit delta x going to 0 will give you dmz by dx, and this term divided by delta x will give you sy plus delta sy. When delta x tends to 0, delta sy will go to 0, so this will simply become sy. The third term qy delta x square by 2, when we divide it by delta x, it will we will be left with qy into delta x by 2, and in the limit when delta x goes to 0, this term will actually go to 0. So that means this will give you dmz by dx plus sy equal to 0. And now if you put the values, so we have already said no dmz is mz is eizz into d theta z by dx, we have already defined. Shear force is ga into minus theta z plus dv by dx equal to 0. So this is the third equilibrium equation. So you will find that now there are three equilibrium equations corresponding to three variables u naught, v and theta z. So when we solve a problem means we have to solve these three differential equations simultaneously. So these are three differential equations and the unknowns are u naught, v and theta z. These are three unknown and they are also primary variables in this case. So these are the unknown primary variables. Now you could actually derive the the integral functional from these differential equations. So I am not going to detail all the steps, but I will just give you a hint. So, but this is somewhat similar to what we had one question in minor. That's the first question. Now I have also uploaded the solution, so you can look at that. Now there is only one additional term over here. So for this, if you look at the better residual statement, although one can write the individual better residual statement for the differential equation 1, 2, and 3 separately, but for the purpose of integral functional, I am writing a combined better residual statement. So this statement we will have is the for the first differential equation. I am taking the weight function directly w1 as delta u. So we will have delta u naught, and then know the differential equation. So we have d by dx. Know the first differential equation, which is ea into du naught by dx, and plus we have qx, and then we integrate over the entire length. So if the length of the element is L, so then this will be integral 0 to L. So no, we were writing individually. So then individually also this term will also be actually equal to 0. This is the weight function which is taken as delta u naught. And then the second differential equation again integral 0 to L. The weight function I am taking directly as delta v. Why delta u is taken here? Because no, you see this differential equation comes from the equilibrium of forces along its direction. So when we write the weighted residual statement, we multiply the delta u naught, which is the the product of unbalanced force, and the delta u gives you the virtual work. So you can say weighted residual statement is kind of giving you the virtual work. And this differential equation comes from this equilibrium of forces along y direction. So we take the weight function as the variation or displacement along y direction, that is delta v is the displacement along y direction. So that is why this delta v is taken over here. And then of course we multiply with the residual, which is the differential equation, all the terms taken to the uh, left hand side. So you have this is ga minus theta z plus dv by dx, and yeah, plus you have this qy and then dx. That's the second term. Individually also this will be 0. Individually this will be 0. Individually this will be 0. But I am combining all three together, and then third equation, if you look at this equation comes from the moment of all the forces about z axis. So we multiply this by the the delta theta z, that is virtual change in theta z, which is actually the rotation. So moment into rotation again gives you the work done, and that is why we are multiplying it by that. So w3 we are taking kind of delta theta z. So we will have delta theta z over here, and then we have the differential equation d by dx of eizz into d theta z by dx, plus we have ga into minus theta z plus dv by dx, and this whole thing multiplied by dx. So this will be equal to 0. The total, I am putting here total, this term plus this term plus this term, all three put together is actually equal to 0. So this is the better residual statement. From this now you can do the integration by parts. So when you multiply this term and this term, then you have to do the integration by parts once. so that you can distribute the derivatives equally between this u naught and delta u naught. And if you look at this term here, so you have to know, when you look at the product of this term and this term, then you have to do the integration by parts once to transfer the derivative from this term to this term. And when you look at this term and this term, you have to do the integration by parts only once to transfer the derivative from here to here. And this term of course will remain as it is, delta theta z dA ga into minus theta z plus dv by dx. So that is how you will obtain the weak form, and then take delta common and get the integral functional. So I am giving you as a homework problem. So just obtain, I have explained you how you are going to do that, but you need to do it. So obtain weak form, identify primary and secondary variables. Although we mentioned that, but from this you argue out, and obtain weak form, identify primary and secondary variable, and obtain integral functional. So this is a homework problem for you. Then now let me go to the finite element formulation. So far we were know that whatever we discussed is applicable to entire structure. Entire in the sense that it is rod, in the sense that length is still much smaller. Total length is much smaller compared to the cross sectional dimensions, but the ratio, like I said, L by H is less than 20. So that we need to use Timoshenko beam theory. If L by H is greater than 20, then you can use Euler-Bernoulli beam theory. So the element we have already discussed. So in this case, now we are going to discuss a two-noded finite element. Two-noded finite element. So in that element, now if let me again sketch the element once. So these are the local nodes, local node number 1, local node number 2, and this is the x coordinate, the local x coordinate, this is local y coordinate. Length of the element is no, small l, and the forces are, now you have, because we are also combining the axial force in this, so you have qx over here, and you have no this qy, so these forces are there, qy is there, and no, left side of this element there would be some other element, on the right side also there would be some other element, so they are going to exert forces, but this is a finite length element, so we denote the cross sectional forces on left and right as the finite quantities, not the differential change in the quantities. So this side is, let us say, q1e, and then the shear force Sy I am denoting as S1e, and the bending moment Mz I am denoting as M1e. And similarly this side we will have Q2e, shear force as S2e, and the bending moment as M2e. This is actually Mz, but Mz I am writing over here as no M, and similarly shear force Sy I am writing simply as S, and with subscript and superscript. So this is as far as the forces are concerned. If you look at the degrees of freedom, so this is the element. This is first node. This is the second node. The degrees of freedom are, at this node you will have degree of freedom u naught 1 for the element, transverse displacement v1e for the element, and you will have theta z. Now theta, I am not writing it as theta because earlier I have used theta as dv by dx, so I am retaining theta z. So theta z 1e. So because in this problem primary variables are u naught v and theta z, so they have to be there as degrees of freedom at the end nodes. And since we are considering a two noded element, so we have to have basically know the 2 degrees of freedom corresponding to each variable at each node. So similarly here you will have u naught 2e, you will have v2e, and the rotation theta z 2e. So these are the degrees of freedom. No, I'm simply writing as DOFs. These are at each node you have 3 degrees of freedom. For the element as a whole, you have got 6 degrees of freedom. Although this is similar to frame element, based on Euler-Bernoulli beam theory, there also we had 3 degrees of freedom at each node u naught v and theta, but there theta was actually dv by dx, and here this theta z is independent of v. It's not dv by dx, but it's a independent variable. So now if you look at the integral functional, so you can directly write as no strain energy and potential of external energy. Of course, when you do the homework problem, you will also know how to get this integral functional from the differential equations. So if you look at the integral functional, the way we have discussed the interpretation of the various terms earlier, so this I integral functional would be half the strain energy, and now the strain energy will have two parts: strain energy due to sigma xx and strain energy due to tau xy. So strain energy due to sigma xx is half integral 0 to L integration over the cross sectional area, and it is half is already there. It is actually sigma xx into epsilon xx, and sigma xx is already e times epsilon xx, so we get it as e times epsilon xx square, and epsilon xx we have defined as du naught by dx minus y into d theta z by dx. So you can write this as e into du naught by dx minus y into d theta z by dx whole square dA dx. So this is the strain energy due to normal stress sigma xx. Then you will also have strain energy due to transverse shear stress, which is non-zero now. So we'll have integral 0 to L integration over the cross-sectional area, and then we have no this is going to be tau xy into gamma xy and tau xy g times gamma xy, so you get g times gamma xy square. So g and gamma xy we have defined as minus theta z plus dv by dx, so you get whole square, and then you have no dA dx. Now what happens is there is another concept here. Basically, as I said mentioned earlier, that this tau xy is equal to g times minus theta z plus dv by dx gives you the constant shear stress through the thickness. Whereas no, in actual, no, if we look at the exact solution, it is parabolic. So to account for that, we introduce a factor which is known as the shear correction factor. So let me put that factor also over here. So I am putting here this ks. Ks is a shear correction factor. I will write again what this ks is. So this is to get the actual strain energy due to transverse shear stress because of non-linear distribution of tau xy transverse shear stress across the thickness of the beam. And then you will have potential of the distributed forces, so you have minus integral 0 to L, and qx is the force, u naught into dx gives you the potential. Similarly, integral 0 to L, you have the force qy into v is the displacement, dx gives you the potential of this. And then you have potential of these internal forces coming from the left and right side beams, so that can be written as u naught 1 v1 e theta z1 e u naught 2 e v2 e and theta z2 e. So now by now you know this is transpose, and the forces are minus q1 e minus s1 e minus m1 e. Axial force, shear force, bending moment on the left, and axial force, shear force, and bending moment on the right. So you will see the potential of the forces on the left side are positive, because this minus and this minus will become plus, and the potential of axial force, shear force, and bending moment on the right side of the beam, that is negative, because work done is positive, potential is negative. So as you know, this we call as the vector of elemental degrees of freedom. So this is actually d transpose, because I have put the transpose over there, and this is f internal for the element. So yeah, this you get as the no basically the integral functional. And now what we do is we carry out the cross sectional integrations, because no the all the unknown variables u naught v and theta z are only unknown functions of x. So everything is known with respect to cross sectional coordinate, so we can carry out the integration with respect to cross sectional coordinates, and therefore we can write this I equal to, again if you look at the when you look at the first term, So when you do the square, you will have du naught by dx whole square plus y square d theta z, d theta z by dx whole square minus 2y into du naught by dx into d theta z by dx. So we are taking symmetric cross section, so the integral y dA would be 0. So we will have only du naught by dx whole square term and d theta z by dx whole square term. So those only terms would remain. So we will have half the cross sectional integration over area will give you cross sectional area. So EA, and then we have du naught by dx whole square dx. The second term of that square, when we open, I said integral 0 to L, we will have E times integral y square dA. Y square dA is, we have already defined, is IZZ, second moment of area of the cross section. So d theta z by dx whole square dx. So this one you will have, and then plus we will have the third term, this one. So that is simply the integration over the cross sectional area, because this factor we are also introducing a constant factor, so everything is independent of y coordinate. So a simple integral ADA will give you the cross sectional area. So we will have half integration 0 to L, integration 0 to L, and you will have G into A into Ks, and we have minus theta z plus dv by dx whole square dx. And then these two can be combined together, so I can write minus integral 0 to L u naught v and theta z put together transpose and qx qy, and of course there can be distributed moment about z axis, so then this would be non-zero third term here, but right now I have put it as 0. So when you take the transpose and multiply, you essentially get these two terms. So this is dx, and the last term is of course minus dE transpose into F internal for the element. So this is what you have, the your total potential energy functional, or you can say the integral functional. Now in this there are some names given. So if you look at the first term, we have already done earlier. So this was appearing in the truss element. So this we call as strain energy. First three terms are basically strain energy terms. So this is strain energy due to stretching, stretching of the middle surface. So the central line y equal to 0 line is stretching. Strain energy due to stretching, and this is bending strain energy, bending strain energy. And if you look at, no, this is this one, this is transverse shear strain energy. And I had also said that this ks is shear correction factor, shear correction for rectangular cross section. This is actually 5 by 6 shear correction factor to account for non-linear, which is parabolic for rectangular section, non-linear tau xy distribution along the cross section. So now what you can do is let me combine these terms together, and this I am keeping separately. Usually we keep that separately because of certain other reasons. So then you can write this integral functional I as half integral 0 to L, and now you want to combine these two terms together. So I am forming a vector consisting of du naught by dx and d theta z by dx. I did this earlier also for the Euler-Bernoulli beam theory based frame element. So it is a similar thing. There we had d2b by dx square, here we have d theta z by dx. So then we have basically du naught by dx and d theta z by dx transpose, and then in between you have a matrix ea 0 0 and EIZZ, and then this side du naught by dx and d theta z by dx. So the first term, no, the strain energy due to stretching and strain energy due to bending are combined together. When you multiply this, you are going to get the same two terms which we have written earlier. And similarly, the shear term we can write as the transpose of two terms, integral 0 to L. We have GA into KS, and then we have minus theta z plus dv by dx transpose into minus theta z plus dv by dx as it is into dx. And then of course you have the potential of externally applied forces qx qy and the potential of internal forces. So minus integral 0 to L, and we have u naught v theta z transpose into qx qy and 0 dx, and minus we have this dE transpose into F internal for the element. So now once you have this integral functional, so the next thing in the finite element formulation, as you know, comes is the uh, interpolation. So now if you look at the interpolation, how do we interpolate? And the variables are three: u naught, v, and theta z. So we are going to interpolate these three variables. Now how do we? So we have discussed earlier, if you remember, there are three conditions. We need to look at the differentiability requirement. So if you look at in the integral functional, highest order derivatives of all the three variables u naught, v, and theta z are first derivative. So whatever we assume as an approximate solution, that has to be differentiable at least once. So that is one. The second is completeness. So we should have a complete polynomial. So if we have constant linear term, we must have a constant term. If we have quadratic term, we must have constant and linear term. And third is that it should satisfy the inter-element compatibility requirement. So in this case, the primary variables are u naught, v, and theta z. Now you remember in Timoshenko beam theory, dv by dx is no longer a primary variable. Whereas in Euler-Bernoulli beam theory, dv by dx was a primary variable, so we needed v to be C1 continuous, that is v and dv by dx to be continuous across the elements. But here no, dv by dx is coming in the definition of shear stress, so it is going like a secondary variable. So primary variables are only u naught, v, and theta z, so they should be continuous across the element. So if we want u naught and v and theta z to be continuous, so that means these u naught, v, and theta z have to be degrees of freedom at the end nodes. And if you look at the end nodes, we have these degrees of freedom. So corresponding to u naught, there are 2 degrees of freedom. Corresponding to v, there are 2 degrees of freedom. Corresponding to theta z, there are 2 degrees of freedom. So in the approximate solution, we should have, as per that, two terms, and then those constants in the approximate solution are written in terms of the degrees of freedom. So that is no the standard procedure. So I'm not going to repeat all the steps, but they are similar to what we have already done. So now keeping all these in mind, we write u naught. Know that when we look at the approximate solution, so we write u naught is equal to a naught plus a1 into x. So it is differentiable once, satisfies the first requirement, and it is a complete polynomial because we have both a constant and linear term, and it has two constants, so that we can have 2 degrees of freedom u naught 1 and u naught 2 at the ends of the element to enforce the inter-element compatibility requirement. Then we say that u naught is equal to u naught 1e at x equal to 0, and u naught is equal to u naught 2e at x is equal to L. And from there we get a0 and a1 in terms of u naught 1e and u naught 2e, and put it back here and get the in terms of shape functions. So we will have n1 into n2, and then you will have no this side u naught 1e and u naught 2e. So this is what no you can get here, already, where n1 is 1 minus x by L. These are the same shape function we derived earlier, and n2 is x by L. So same thing we will assume for v also. Say some another set of constants b0 plus b1x, and then we will be writing these two in terms of the same shape function in n1 n2 into v1e v2e. So again, the say b0 and b1 are written in terms of b1 and b2. The same shape function n1 and n2 come over here. If you remember, the in the frame element based on Euler-Bernoulli beam theory, we had interpolation for u naught in terms of n1 and n2, but v was in terms of Hermite interpolation function, because there v and dv by dx they are primary variables. Here only v is a primary variable, so the interpolation for v is same as what we have the interpolation for u naught. So similarly, when you look at theta z is also is a primary variable. So it has to be basically differentiable once, and so you can assume it to be c0 plus c1x, and c0 c1 written in terms of theta z1e and theta z2e, and therefore finally it would be in terms of n1 n2 into theta z1e and theta z2e. So yeah, this is the interpolation. Now if you put all the three together, so usually in finite element we write all the variables together. So we have u naught, v and theta z. So I want to write the interpolation of all the three variables together. So we will have an interpolation matrix, and we will have vector of elemental degrees of freedom. So vector of elemental degrees of freedom is u naught 1e, v1e, theta z1e, u naught 2e, v2e, and theta z2e. So this is a 6 by 1 vector, as you know. So for the element there are 6 degrees of freedom. There are 3 nodal degrees of freedom: displacements along x, y, and the rotation about z axis. Keep in mind, this is a displacement along x, displacement along y, rotation about z axis. So two translation and one rotations are the degrees of freedom over here at each node, and for the element as well 6 degrees of freedom. Now I want to write u naught. So u naught is simply n1 into u naught 1e plus n2 into u naught 2e. So they say u naught 1 is first variable and u naught 2e is the fourth variable. So this n1 and n2 has to be written at first and fourth location. The other terms will be 0. Then v is nothing but n1 into v1e plus n2 into v2e, and that is at location 2 and 5. So we put n1 and n2 at location 2 and 5, and we get this 0. And theta z is n1 into theta z1e plus n2 into theta z2e, and theta z1 is at location 3 and theta z2 is at location 6. So we put 0 0 and 1 at third location, 0 0 and 2 at sixth location. So we call this now the matrix as is the interpolation matrix. The names are same, so I'm not writing again. So this is your interpolation matrix, and this is the vector of elemental degrees of freedom. So the nomenclature is the same. So that is one we have, and then in the integral functional, if you look at, we have this du naught by dx and d theta z by dx, and also this minus theta z plus dv by dx. So we'll also have to write these in terms of derivatives of the shape functions and the vector of elemental degrees of freedom. So we write du naught by dx and d theta z by dx. So this is equal to, again we are writing in terms of the same degrees of freedom and the shape functions. So degrees of freedom are same: u naught 1e, v1e, theta z1e, u naught 2e, v2e, and theta z2e. So first term is du naught by dx. So I know it's basically going to be just the derivative of n1 and n2. So we will have dn1 by dx 0 0, dn2 by dx, and then again 0 0, and then we have d theta z by dx. So 0 0, we will have dn1 by dx 0 0, dn2 by dx. So now let me call this as B matrix B, and that is simply DE. So this is your B matrix and this is D. D we have already defined. Now we have another transverse shear strain. So we have this gamma xy. So gamma xy is minus theta z plus dv by dx. So you already know that. So this is only one node term. So we'll have just a row here, and this side will have same 6 degrees of freedom for the element, that is dE. So now this is basically, if you see, dv by dx minus theta z. dv by dx would be written as dn1 by dx into v1e plus dn2 by dx into v2e. So u naught is not coming, so that term will be 0 here. So we will have 0 here, and then we have b1e term which is going with dn1 by dx, and then we have theta z which would be minus n1 theta z1 minus n2 theta z2. So we'll have here minus n1 again 0, and then dn2 by dx and minus n2. So this will be the matrix for the interpolation of transverse shear strain. This I am denoting as Bs, and this is of course is D. Bs is this matrix. So now you will see this Bs involves uh, derivatives of the shape function and also the shape functions themselves. So this is the first column, second column, this is third, fourth, fifth, and sixth. So you can notice what are the sizes of these various no the matrices and vectors. And this is a 6 by 1 vector as you see over here. So now if you look at the no element level governing equation, so yeah, the element level governing equation, if you look at, we are going to have that as, I'm not going to derive now. You should be able to derive that. So we substitute all of these interpolations. So and then no take the variation of I. So element level governing equation. So what you are going to do, whatever interpolations we have assumed, you are going to substitute that. So we will have half integral 0 to L, then we will have no D transpose into B transpose. So if you look at over here, no, this integral functional. So you have this du naught by dx d theta z by dx transpose. So there they would become D transpose into B transpose into this matrix, and then B into DE, and this will become D transpose into BS transpose into BS into D, and like that. No, so now by now I think you should be no aware of all this. So this will be here. Of course, we have EA 0 0 and EIZZ 2 by 2 matrix with diagonal elements, and then here we'll have B into DE dx. So this is one term plus half integration 0 to L. The second term we have DE transpose, and then we have no, you can write of course this GAKS anywhere, and then we have no this BS transpose into BS into DE or dx, and then minus you have integral 0 to L or DE transpose into H transpose, and into this QX QY and 0 we have dx, and of course minus dE transpose into F internal. So this is what you get as your I. Then what you do, you take the variation of I. So delta of I, no, the for equilibrium, the equilibrium satisfaction of the equilibrium equation is equivalent to, so the satisfaction of the equilibrium equations uh, is the equivalent to delta I equal to 0. So for equilibrium delta I must be equal to 0, and then you take the delta I and then delta D transpose common on the left hand side, and that is arbitrary. So the delta I should be 0 for all values of delta D, and that gives you basically the element level governing equation, which is Ke into DE is equal to F external for the element plus F internal for the element. And here now if you look at the Ke, so I let me define each of these matrices. So Ke will be equal to integral 0 to L, we will have B transpose into EA0 EIZZ into BDX, and plus even now the stiffness will involve two terms, so the transverse shear contribution will also be there. So integral 0 to L, we will have GAKS into BS transpose into BS dx. So this is going to be the stiffness matrix. Now the stiffness matrix is coming in terms of two variables, two terms, this matrix plus this matrix. We have already defined B, BS and everything, so you should be able to calculate finally what is these stiffness matrices. And F external for the element will be So we'll see that f external will be equal to integral 0 to L. We will have H transpose, and then we will have Qx, Qy, and 0 dx. So if you look at the various sizes, so K is going to be 6 by 6. This is 6 by 1 vector. This is 6 by 1 vector. 6 by 1. F internal we have already defined. Now if you look at B transpose is a 6 by 2. This is a 2 by 2 matrix, and this is 2 by 6. If you look at this, BS is just 6 by 1, and this is 1 by 6. So finally gives you 6 by 6 matrix. H is 3 by 6. H transpose is going to be 6 by 3. This is 3 by 1. So finally we'll give you 6 by 1 vector. And then you have finally, I just said, no, if you look at the F internal for the element, although we have already defined, but let me write it again. So minus Q1E minus S1E minus M1E, then you have Q2E, S2E, and M2E. So this is F internal. So this gives you the basically element level governing equation. So I think, yeah, this is where I want to stop. And only thing is, again, another homework you should do. Homework of evaluate KE F external, KE and F external for constant EA, EIZZ, and GAKS along length of the element. So basically you have to take, these are, assume that these are constant. The shape functions are already defined. dn1 by dx would be minus 1 upon L, dn2 by dx will be 1 upon L, and n1 n2 are defined. So you should try developing finally what is the form of K and F external. And once you have this, then you should be able to solve problems. So I think now I will not be discussing problems no on this. I expect that no, you should be able to solve problems given this element and the stiffness matrix load vector and all is given. So you should be able to solve this. So I think I want to stop here. And if I think, yeah, only Deepak and Abita are there. So Abita, if you have any questions, you can ask. Deepak. The Navy students have not joined today because they have afternoon some exam, so they would be watching the videos afterwards. So, but morning I had some urgent work, so that is why I could not take the class. Abita, any question? Okay, so then thank you for attending this class. I stop here. Thank you all. Thank you for your attention.